Hi everybody. In the last video we finished talking about Jupiter's moon Io, and in this video we're going to talk about Europa, the second of the Galilean satellites and in many ways the most interesting. So let's get to it. This is a true color picture of Europa taken by the Galileo spacecraft. As you can see, it has very few impact craters. In fact, in terms of large ones, we only see one. This one right here, it's called the Quill crater. And here we can see a little bit more detail if we look at enhanced color. But this moon is mostly covered with ice, as well as some other molecules and compounds, some of which are organic. So, a little bit of trivia. The gravity on Europa is a little less than that of our moon. It's just a little bit smaller than our moon, but if you were to put it in place of our moon in the night sky, it would appear much brighter because it's a lot more reflective than our moon. Our moon actually has a reflectivity similar to that of asphalt, whereas Europa has a whole lot of ice. Now, surface temperature there is quite cold, but underneath about 10 kilometers or so of solid ice is a liquid ocean that has about 2 or 2.5 times as much liquid water as all of Earth's oceans combined. And it's salt water like Earth's oceans. I mean, you don't want to drink the water in our oceans, that would be bad. But nonetheless, it does have one of the youngest surfaces of any solid object in our solar system because of the fact that it is constantly being resurfaced due to geological processes. So this is a very basic view of its internal structure. We'll get to the more detailed view soon. But it has a solid core and then a mantle. And then above that, it's the liquid water ocean and then a thin icy crust. Now, there's been debate for some time about the actual thickness of the crust itself, where it could be anywhere between 5 kilometers and 50 kilometers on average. What we do know is that there are some places where it is very thin, and there are other places where it's probably a bit thicker, though exactly how much thicker it's hard to say. But nonetheless, the ocean itself is very deep once you get into it. So, particularly around the South Pole, the ice is thin enough to allow for water to come to the surface occasionally. In fact, we have seen eruptions in that area in the past few years. So here's a picture of ice rafts and the Quill crater. We'll have more to say about those ice rafts very soon. Now, as you hopefully recall, Io, Jupiter's innermost Galilean moon, its innermost large moon, has a very slightly elliptical orbit due to the fact that it's constantly getting tugged by Europa and Ganymede at the same spot in its orbit, like a child being pushed on a swing. So what this means is that there are changing tidal forces affecting Io. If it was always the same tidal force, it would always be distorted to the same shape. But because of the fact that there are changing tidal forces on Io, Europa's shape gets distorted differently depending where it is in its orbit, and that changing distortion generates a lot of heat. Well, the same thing happens with Europa. It's just one problem. It's significantly less on Europa than it is on Io. It's stronger on Io, weaker on Europa, because Europa is a bit farther from Jupiter. Remember, the magnitude of the tidal force goes as 1/4 distance cubed from an object. So it's quite a bit weaker on Europa. In fact, that by itself should not be enough to generate enough heat to give all of that sustained global liquid ocean that Europa seems to have. But there is more to it than that. In fact, the primary cause of the heating in Europa's interior is actually a resonance due to the differing tidal forces, because as the tidal forces change as Europa goes around, that generates waves which end up going from one end of the moon to the other end of the moon. And these waves, which we call Rossby waves, are actually generated at the same rate as it takes them to go to traverse the moon. So it's like another one of those resonances, kind of like a child being pushed on a swing. In fact, these account for 200 times as much heating as just the frictional heating from the changing tidal forces alone. So perhaps if Europa had a considerably different size, it wouldn't work at all because you wouldn't have that resonance. Although the truth is, resonances tend to kind of come about when they can. And if Europa had a different size, my guess is that Europa's crust would have a different thickness, and you would still end up getting the resonance. So in other words, the resonance works except where it doesn't. But where it does, it works. So these are the primary power source for Europa, but it still has something to do with the changing tidal forces, combined with the fact that Europa has a slightly tilted axial tilt. So in any case, you end up getting these waves, which end up by themselves in this resonance, producing a lot of the heat as the energy of the waves dissipates. In either case, the result is that you get a lot of internal heating for Europa, and this internal heating can create a lot of volcanic activity. So in the case of Europa, unlike Io, the volcanic activity doesn't make it to the surface because Europa, remember, formed farther from Jupiter. And since it formed farther from Jupiter, it kept a whole lot of its volatiles, water, sorry, allergies. But yeah, these volatiles, like water ice, end up being in much greater abundance on Europa. So that gives it a what would otherwise be a very, very thick icy crust. But because of the fact that the mantle is providing a lot of heating, the part underneath that is melted into a global ocean. Of course, near the surface, the temperature is very, very cold, 50 kelvins to 125 kelvins, depending on your location. So at the very surface, it freezes. But occasionally, enough convective heat rises to the surface to allow fractures where you get liquid water forming. In some cases, actually, lakes somewhat similar to some of those liquid lakes under the frozen ice of Antarctica. Frozen ice, yeah, I know that's a redundancy, but whatever. So an important difference is that in the case of Earth, where you get these kind of ice rafts that I showed, those tend to be weeks or months old, whereas on Europa, some of those ice rafts are hundreds or even thousands of years old. But here's a very nice high-resolution picture of some of these ice structures from where you get enough heating to bring some liquid to the surface and cause fracturing. By the way, notice back here, you have, what's this? A discontinuity. Europa has effectively active plate tectonics. There are two other bodies in the solar system other than Europa that have active plate tectonics. You can probably guess one of them, but you might not be able to guess the other one, and we're going to get there. So here are ice rafts on Earth compared with those on Europa. And then again, here you see some more of those tidal stresses from these plate tectonics. In the case of Earth, the plate tectonics are from this rocky crust. In the case of Europa, they are along an icy crust over a big liquid water ocean. So in terms of the thin ice model, you have quite a lot of convection making its way to the surface, whereas with the thick ice model, the convection isn't quite so strong. Maybe the temperature at the top of the, I guess you could call it kind of a mantle, so to speak, is a little bit less, and we're not completely sure which model is 100% correct. What we do know is that aspects of both of these are relevant in different areas of the moon. Here is the depiction of how plate tectonics works on Europa. You have subduction zones, and you also have these strike-slip faults in different areas of the moon, where you end up getting, we see that because of the fact that there are shifts between certain crustal fractures that are older due to the movement of these crustal plates, so to speak. So again, Europa is one of only 3 known bodies in the solar system that have this. The other, as you can probably guess, is Earth. One other is. But the third one, you might not guess, is actually Pluto, dwarf planet Pluto. So those are the only 3 bodies in the solar system known to have active plate tectonics right now. Now, there are certain areas on Europa where the structure of those ice features tells us that it has simply collapsed into these kind of lake areas that get heated by convection that gets trapped. So you'll have these pockets of lakes in certain areas of the ice. We're talking big lakes here. And the fact that there is this recycling of material between the surface and these lakes, and then also between, over a long time, these lakes and the global ocean underneath, leads many scientists to suggest that this is a prime place to look for life in our solar system. Because you can develop life around these so-called black smoker regions near these undersea vents. That may be how it developed on early Earth, but it's hard to evolve significantly unless you have a recycling of nutrients between the surface and the under ice areas. But we do have that on Europa. We also probably have that on Saturn's moon Enceladus, but we'll talk about that in a future video. Geysers. In late 2013, there was evidence of geysers found with the Hubble Space Telescope, at least when scientists were pouring through those data, and spectral sampling of a vapor plume emitted in 2012 showed that it had water vapor. So this was not present in images that were taken in November 2012, but it was present in images taken in December of 2012. So a very remarkable result. Some of you may already know that Enceladus is known to have these water ice geysers. They have been photographed when the Cassini spacecraft was investigating that moon in great detail. Well, now we know that Europa has it too. So here's an artist's depiction of this. Now, the idea is that you have the ocean, and there's enough heating under the ocean to create enough pressure that in certain areas, particularly around the poles, that pressure is able to break through the ice, and you get these geysers that blow out not only water ice and water vapor and stuff like that, but also a bunch of other things, including some organic molecules. So that's especially an issue also on Enceladus. So the idea is that this ocean is kept warm by these hydrothermal vents, the black smokers that are in great abundance in Earth's oceans as well. And also you'll occasionally get meteor impacts. These meteor impacts are what bring in often quite nutrient-rich material. In some cases, things like amino acids and stuff like that. Yes, we have discovered lots and lots of amino acids in newly fallen meteors or meteorites, including amino acids that don't exist naturally on Earth. So again, Europa and Enceladus are considered the two top places in our solar system by many scientists and astrobiologists to search for life outside of Earth. So the reason that these moons rank so high is because of the fact that there is, one, lots and lots of liquid water, and two, a recycling of nutrients between the surface and the underpart. Now, a planned future mission to Europa is NASA's Europa Clipper, and there is a lander built into that budget where the lander would end up kind of just directing itself around via LiDAR or something similar, and would potentially at least study samples. It wouldn't return samples to Earth, but it would have the capability perhaps of studying these samples to reveal what kinds of organic molecules are on the surface. So there are 5 main reasons why scientists are so excited about the possibility of life in Europa's global ocean. And essentially you can think of this as something of a summary of our discussion about Europa. First, Europa has lots of water in liquid form under its crust. And it also has essential elements, carbon, hydrogen, oxygen, nitrogen, that are essential for making biological compounds for life as we know it. And it has an energy source, those hydrothermal vents all around under the surface that are helping to keep not only helping to keep the ocean liquid, but also spewing out all kinds of other, I guess you could call them vitamins and minerals potentially. And it has a long-term stable environment, giving life time to evolve, and also kind of going along with that, you have this recycling of nutrients between the surface and the subsurface. And 5, there is protection from harmful solar radiation, because in the case of newly developing life, having an icy crust like that can actually be quite helpful. In the case of Earth, we have an atmosphere which helps to protect us from that harmful solar radiation. and a magnetic field, which helps to prevent the most energetic particles from really doing much damage, at least to us. But nonetheless, I mean, Europa, of course, doesn't have a very strong magnetic field, but it does have that protection in the form of that icy crust, but nonetheless not so thick that it prevents nutrients from being recycled from the surface to the underparts. Okay, so that is the end of our discussion about Europa. If you have any questions or comments, please put them in the comments section on YouTube. In our next video, we will finish off our discussion of Jupiter's moons, starting with Ganymede, the biggest moon in the solar system. So I hope to see you then, and thank you for watching.